Let's continue the discussion about finding antiderivatives. And so to start off, just once again, a projection of our table of antiderivatives that are coming out of all of the derivative formulas we have, and now just working our way backwards, starting with a function and now looking for the function whose derivative that is, looking for the antiderivative of the functions. So let's go ahead and take a look at this function. So here we start with a derivative, f prime of x. And we are asked to find f of x. We are given the notation and asked to find the prime notation and asked to find the antiderivative. So to find the antiderivative, we're going to have to look at this function, cosine of x minus 4x, and apply our rules. So we're looking for the function whose derivative is the cosine of x, right? We're going the opposite. We're taking the antiderivative, and that would be the sine of x. Then we also have that minus 4. Again, remember we can do antiderivatives term by term, just like we take derivatives. And when we have 4x, this is 4x to the first. So this is going to become x to the second divided by 2. Now, of course, we have a constant. This is the general antiderivative, so we have that constant. But this time, we have some additional information. So, you know, if we had no other information, we would simply simplify that one term, 4 divided by 2 minus 2x squared plus c, and we'd be done. But now we have enough information that we could actually find that c. And so that's what we're going to do. So now we're going to say, oh, but f of 0 is 3. So we use that information. F of 0 would be sine of 0 plus 2 times 0 squared plus c, and that is equal to 3. So that means that c, because of course all that just zeroes out, c is equal to 3. So my answer here, given that specific information, we can find not just the general antiderivative, but the specific antiderivative that satisfies the condition that was given. And we can always check, right? We could always do a quick check, take the derivative, make sure we're right. Take f prime of x, and we would get cosine of x minus 4x plus 0. And so we have our check. We won't always check, but I do always like to remind you that if you're ever wondering, did I get the right antiderivative, just check it, take the derivative. You have the ability to do that pretty easily. Okay, let's take a look at another example. So once again, we are given f prime of x and asked to find f of x. So that's finding an antiderivative. So we need to find the antiderivative. F of x. We have to think about what function has a derivative of 5 over 1 plus x squared, and that is the inverse tangent. That is the inverse tangent of x. That is exactly what, well, let's write it this way, 5 times 1 over 1 plus x squared. The derivative of inverse tangent of x is 1 over 1 plus x squared. So if it helps to kind of pull that constant out so that you can see it there, we could. Now, of course, we have a constant, so plus c. But again, just like on the last example, we have a little initial data, a little information about the specifics of this function, so we can plug those in. So now we plug those in, and we can say, well, f of 1 would be 5 times the inverse tangent of 1 plus c, and that is going to be equal to 7. Now the inverse tangent of 1 is pi over 4 plus c equals 7. So c is actually 7 minus 5 pi over 4, that constant. We approximate it, I guess, if we wanted to, but I'm going to just leave it. So f of x, give the exact answer, is 5 times the inverse tangent of x plus 7 minus 5 pi over 4. And there is my antiderivative. Take the derivative of that, and this one I'm just going to say verbally. Take the derivative of that, and you get 5 times 1 over the quantity 1 plus x squared plus 0, because all of this constant over here at the end just would zero out. We have the antiderivative. All right. Let's look at one more of these, and then we'll get into a specific context. So let's take a look at this guy. Let's make that a little bigger. It's really small. So this time, we are told that f of x is, find f of x if f double prime of x. So check that out. F double prime, we're actually going to have to do repeated antiderivatives. we have to do a couple of antiderivatives in order to go from f double prime all the way back to f of x. So if we start with f double prime of x equaling x squared plus, and I'm going to write this as x to the negative 2. 1 over x squared is x to the negative 2. We are told as well that x is greater than 0, so we'll keep that in mind. Then we're given a couple of pieces of data. We're told some information about the function and about the derivative. So we're going to have enough information here to find those constants as we go, but we have to kind of take it in steps. So let's take it in steps. So let's first find the first antiderivative. So to go from f double prime backwards to f prime of x, we'll take one antiderivative. So we'll apply that power rule. This will become x to the third divided by 3 plus x to the negative 1. Remember, we add 1 to the power and divide by that new power, negative 1, by the n plus 1. Okay? So we add 1 to the power, so the power becomes n plus 1, and we divide by n plus 1, plus a constant c. So f prime of x is equal to x cubed over 3 minus 1 over x plus c. Okay? Now we could leave that constant here and take another antiderivative right now to find f of x, but then f of x would have that constant plus a new constant through the next process of finding the antiderivative. So let's instead come up here and see, is there a way that I could find the c? And it turns out that there is a way to find that c. I can use the info given. So let's go ahead and do that. So f prime of 1 would be 1 cubed over 3 minus 1, so it's going to be 1/3 minus 1, plus c is equal to 2. So let's continue to find c. So this becomes negative 2/3 plus c equals 2. Add 2/3, so c would be 2 plus 2/3, but that would be 6/3. So c is actually 8/3. Okay? So we can put that information together and we can say that f prime of x is equal to x cubed over 3 minus 1 over x plus 8/3. So we have this. We started with the second derivative with a little bit of information and antiderivatives. We have found the first derivative, and now we have to go one more step, find another antiderivative, find f of x. So f of x is going to become x to the 4th over 3 times 4, because we're going to have 3 times, we're going to divide by 4 as well. So it'll become 12 on the bottom there. Now notice that this 1 over x, that is the one special case when x, that's x to the negative 1. Okay? That becomes a natural log. That is a natural log of the absolute value of x. And then, of course, a constant, 8/3, is going to become 8/3 times x. Now, we also have a constant through that process of antiderivatives. I'm going to use a capital D. Use any letter you want. We could have, over here with the c, we could have called c1, since we knew we were going to have to take more than one antiderivative, and then called this c2. But somehow denote that it's an unknown constant, I'm going to go ahead and use d in this case. So it turns out that my function is actually x to the 4th over 12 minus the natural log of the absolute value of x plus 8/3 times x plus d. And we are almost done, except for the fact that we also had some information here that we can use to find d. So we can use, again, we can use the info given. So they're a little like puzzles, right? We use our process of antiderivatives, and then we use information to plug in and piece it together. So f of x, f of 2 would be 2 to the 4th over 12 minus ln of the absolute value of 2 plus 16/3 plus d, and that is equal to 3. So 2 to the 4th is 16, so this is 16/12 minus ln of 2 plus, we could drop the absolute values actually, we don't need, the absolute value of 2 is 2, plus 16/3 plus d equals 3. Just doing a little bit of algebra here. This is going to reduce, the 16/12 is going to reduce to 4/3. And let's see here, we can add those, so we get 20 thirds minus ln of 2 plus d equals 3. If we're going to subtract those over, so d would be 3 minus 20 thirds plus ln of 2. And let's just go a little bit further here. So this becomes 9 thirds minus 11 thirds plus ln of 2. And we could leave it, there's nothing more. We could approximate it, of course, but that is our d value. So we have found, ultimately, through all of those calculations, 2 antiderivatives, and some substitutions to find the constants, we have found that f of x is x to the 4th over 12 minus ln of the absolute value of x plus 8 thirds x minus 11 thirds plus ln of 2. And that is our antiderivative. So now that we've had some practice with antiderivatives, let's talk about a very specific application to antiderivatives, and that is our connection between position, velocity, and acceleration, one that we've worked with, and we've utilized the relationships through taking derivatives, s of t being our position function. Take the first derivative and you have the velocity function. Take the second derivative or the derivative of the velocity function and you have the acceleration function. So these are functions that we are familiar with. Now, working the other direction, now we can actually, we have up to this point, I should draw the arrows the other way first. Up to now, we've only gone this way, right? We've started with the position, come up with the velocity, taken the velocity, come up with the acceleration, and answered questions based on a context in the problem. But now we're actually going to be able to go the other direction. We're going to say, now that we have antiderivatives, we could start actually with any of these and create the other two. So we could start with acceleration and work our way back to position. Right now we can start down here with acceleration and work our way back to position by taking 2 antiderivatives and use some information about the problem given. Or we can start with velocity and work our way to position, or start with velocity and go down and work our way to acceleration. So we have some more flexibility now that we've defined antiderivatives. So we're going to add one more piece in here, and we're going to say this. It turns out, we're going to talk about objects that are dropped or thrown. And it turns out that gravity works on objects that are close to the Earth's surface. So if we, and by close to the Earth's surface, like in any kind of human capacity, right? Like we're not like floating out on a satellite. So if we're working on the Earth's surface in such a way that force of gravity, if there's no other force acting on it, if there's no other force, like no rope pulling on an object or anything like that, there's no other force working on the object, then acceleration due to gravity is going to be a constant. And these are 2 numbers that you're going to need to know. In my course, of course, you don't necessarily need to memorize these, but we will utilize them enough that you probably will. Take a physics class, though, and you're going to need to memorize these. One of these is in the metric system. So the negative gravity in the metric system is negative 9.8, sometimes negative 9.81, depending on how many significant digits you want. So here is your metric system gravitational force, and in the US standard, feet and seconds, the gravitational force is negative 32 feet per second squared. In the metric, it's negative 9.8 or negative 9.81 meters per second squared. So these will be our 2 conventions. And if we're talking about an object that is either thrown or dropped, it will have only the force of gravity working on it, and so its acceleration will be equal to one of these constants, depending on which system we're working in, if we're talking in feet or if we're talking in meters. Okay, so simply using that fact, knowing that that's what our acceleration would be, that constant gravitational force, we can use that to find a bunch of other information, right? Like, and we might have a little more information about the scenario, and then we can piece it all together. So I want to do, I think we'll get through at least 1 or 2 examples on position in this video. So let's start with this one. Suppose your calculus book is dropped off a 60-foot building. Now, when you say the word drop, that means that it is released from your hand with no velocity. So there is no initial velocity. So when you drop an object, the verbiage there means that there is no initial velocity. That is also stated here, but sometimes it's not, and so I want to mention that. Okay, so it's dropped off of a 60-foot building. It has no initial velocity, which when you say that it is dropped, unless some velocity is given, the assumption is that it is just released from your hand, right? There's no velocity. It doesn't start with any speed. It immediately, instantaneously starts to gain speed because gravity starts to pull it back down to Earth. Okay, so let's zoom in here a little bit. It's pretty small. Let's determine the position function and when, meaning the time, that book hits the ground. Okay, so we got to piece together the information that's given here. We are working in the U.S. standard system. And in the U.S. standard system, acceleration will be equal and opposite to the force of gravity because gravity is pulling it down to Earth. So A of t is going to be negative 32 feet per second squared. Okay, that's the concept we just talked about. We are also told that there is no initial velocity. So that means that v of 0, that's velocity at time 0. So v of 0 is equal to 0. We could put units on it. That's in feet per second. We are also told, sort of in the context, that the position s of 0 at the initial time is 60 feet. Okay? So we have acceleration, we have initial acceleration, initial velocity, and initial position. So now, pulling all this together, along with what we know about the relationship between position, velocity, and acceleration, and what we now can do with antiderivatives, we can answer our questions. So the first thing we're going to do here, we're going to go from acceleration to velocity. So velocity, this is just a constant, so this is going to be negative 32t plus a constant, plus c. Well, how am I going to find c? Well, I'm going to plug in my data here from initial velocity. V of 0 equals 0. So plug that in, and that's going to turn into c is just going to be 0. So that means that our velocity function is simply negative 32t. Now, velocity, by the way, is measured in feet per second, so I could put the units back on. So we started with acceleration. Now we've gotten to velocity, and we have one more step here, one more antiderivative, because we need to find the position function. It says find the position function. We would need it whether it said find it or not, because to figure out when the book hits the ground, we need to know when the position is at 0, when it's on the ground. So we will find once again, we're going to find an antiderivative, right? Each of these little red arrows here, we're finding an antiderivative. And so the position function is going to be negative 32t squared, because this is t to the first, divided by 2, plus another constant, so plus t. So s of t is negative 16t squared plus d, and we know enough information because we are told that the building it was thrown off of was 60 feet. So let's plug that in. So s of 0 equals negative 16, 0 squared plus d equals 60, and you can see pretty quickly that d would have to be 60. So our position function is negative 16t squared plus 60. Okay, so really quickly, just with a little bit of information, we were able to generate all three of those functions based on just, laws of motion, a force. An object, when dropped with no other forces acting on it, has that acceleration due to gravity. And then using antiderivatives and some initial data here, and we have the position function. So now we can answer the question, when does it hit the ground? So when does the ball hit ground? Well, the ball would have to hit the ground when the position is representing its height off the ground, so when the position function equals 0. So when does negative 16 t squared plus 60 equals 0? So that's when t squared equals 60 over 16, or 15 over 4. So when t is equal to plus or minus the square root of 15 over 2, obviously the negative time doesn't give us anything legit. So 15 over 2, so it's going to happen at approximately 1.94 seconds. So you could warn people below you before you throw the ball down. Now that you're going to throw your calculus book down, you can now you can warn the people below you not to be around, around 1.9 to 2 seconds, so they don't get hit in the head by your calculus book. Okay, so let's end this video out with just one more example with acceleration, velocity, and position. So let's suppose that a car is traveling at 72 miles per hour when the brakes are fully applied, producing a constant deceleration of 25 feet per second squared. One thing to notice here is the difference in units, miles per hour and feet per second squared. So we're going to have a little bit of conversions happening here as well as we do this problem. So just something to notice as you're reading through the problem. What is the distance traveled before the car comes to a stop? So let's write down the information that we're given. So we're said that we have a constant deceleration of 25 feet per second. So that's our acceleration. Our acceleration is a deceleration, so negative 25 feet per second squared. So that's given. We are also told that the car is traveling at 72 miles per hour. So that's the initial velocity when this acceleration is applied. Deceleration, I guess. So v of 0 is 72, and I'm going to go ahead and write that in miles per 1 hour. I'm going to do that because we are going to have to convert that. So let's do a quick little conversion on that. We need to get that into feet per second. So to convert that, this is a nice little conversion review. We got to convert the hours into seconds. So in 1 hour, there are 3,600 seconds. And in we got to also convert the miles into feet. So in 1 mile, there is 5,280 feet. So it turns out actually that v of 0 for our purposes, I would go ahead and multiply that together and reduced it. It's 528 feet per second, which is actually equal to 105.6 feet per second. Okay, so that's the velocity that we're starting at when we hit this acceleration, the deceleration. Okay, so we can start working our way through some antiderivatives now. So, because again, we want to know a distance traveled, so we ultimately need a position function. So we got to get our way to a position function. So let's start working our way through some antiderivatives. Let's do an antiderivative to find the velocity function. So the velocity function v of t is going to be negative 25t plus c. But we also know the initial velocity. We know the I just caught real quick, I had a little mistake right here. This should have been 5 seconds. I was copying down from my calculations on a piece of paper and I forgot to write 5 seconds. So that should have been 528 feet for every 5 seconds. So what we can do now is come back over here. We know the initial velocity, that's our initial velocity in feet per second. So we can plug in 0 and we can find that c has to actually be equal to that. And I'm going to go ahead and use the exact answer here. So we could put in the decimal. That is the exact decimal, actually 105.6. But I'm going to use fractions. So c is actually, obviously that zeroes out, so that is the c value, and we can plug that in. So v of t is negative 25t plus 528 over 5. All right. Now all we have left to do to find the position is to take one more antiderivative. So we're going to take one more antiderivative and find the position function. And the position function is going to be negative 25 t squared over 2 plus 528 over 5 times t plus another constant from when we take the antiderivative. So we are taking the antiderivative of the velocity to find the position. Okay, but now we need to find that d. But remember that our initial position, this deceleration was applied when we were at a position of 0, right? We're trying to figure out how, once this is applied, how far we'll go. So we didn't write that up here at the beginning, but we could very well have just said that the initial position is position 0. So this d ends up having to be equal to 0 as well, because s of 0 would be d, and that has to be 0. So d ends up being 0. So our position function, s of t, is negative 25 t squared over 2 plus 528 over 5 t. I'm trying to grab my highlighter. It's not letting me grab my highlighter here. Okay, well, let's just try to wrap this up. Let's not worry about the highlighter there. All we have left to do now is to figure out when the car stops. Well, the car stops when the velocity is 0. So when is the velocity, when is v of t equal to 0? So we're trying to figure out how long does it take the car to stop from that speed of 72 miles per hour. So when is v of t equal to 0? So we set v of t equal to 0, negative 25t plus 528 over 5 equals 0. And because my screen is starting to freeze up on me, I'm going to make this really quick. Solve that ahead of time, and that was when t is equal to 4.2 seconds. So it takes 4.2 seconds to come to a complete stop with that type of deceleration. And so how far do we travel? Well, s of 4.2, when we plug that into our position function, we would end up with around approximately 223 feet. And that's how far it takes to stop. So it takes about a little over 4 seconds to stop, and the car would travel 223 feet in order to do that. Okay? And so at the end there, my screen was freezing up a little bit, but let me scroll out. I think we get the general idea. So using antiderivatives and some ideas about motion, and right, obviously if you're at a stop, your velocity is 0, your rate of change is 0.